Hello YouTube. Today we will be covering the heat conduction equation from partial differential equations. So, what is a partial differential equation? Well, let's first cover what an ordinary differential equation is, kind of. So in ordinary differential equations, we could have let's say a spring and that's attached to a box that moves back and forward like this. And we'd be able to model it with ordinary differential equations, which are differential equations that you're able to vary with only one variable. So in this case, it's x. Note that the rest of these are just constants. So ordinary differential equations are mainly concerned with how the dependent variable, which is d, affects the independent variable, which is x. So in a partial differential equation, you'll have multiple variables that cause our independent variable to change. So instead of a spring that moves a box back and forward, now think of a heat bar, like a bar of metal that conducts heat. And let's say its heat distribution when time is equal to 0 is equal to x. Now, let's say suddenly you change the temperature of both ends of the rod to be 0 degrees Celsius. Well, since the function f of x of 0 and 0 equals x, there's not a constant temperature distribution throughout this bar, and it's not like temperature stays constant over time either, because there's going to be 50 degrees, it's going to be 50 degrees here, 10 degrees here, and this point in the bar is affected by the other points. So this is 8 degrees here, this is 12 degrees here. These 8 and 12 degrees are going to change this 10 degree to be more like them. And then the 12 degree is going to be affected by the 10 and 14. This 8 is going to be affected by the neighboring one, so 6 degrees, the 0 degree over here. So it's just kind of crazy. And all this can be modeled with a differential equation with two independent variables instead of just one. And that kind of makes it tricky. So later in this video, we'll learn how to solve the heat conduction differential equation. So the partial differential equation in question is alpha squared times the partial differential of u, which is our solution to the differential equation, the second partial of u with respect to x, that's equal to the first partial of u with respect to t. So u is basically going to be our temperature distribution throughout a one-dimensional rod. Maybe later we'll cover two-dimensional slabs, but for now we'll just cover one-dimensional bars. And for this video, for simplicity purposes, we'll just cover how to solve for bars where this u is equal to 0, this is equal to 0. So what this means is that when time is equal to 0, because note that u is a function of x and t, so when time is equal to 0, this point x equals 0, the temperature here is 0, and at this point x equals L, which is the length of the bar, the temperature is also equal to 0. And in a future video, we'll cover a more general case and how it could reduce to this form. But for now, we'll just cover functions with these boundary conditions. So u of 0, 0 equals 0, and u of L0 is equal to 0. Okay, now let me go more in depth on what I was saying at the introduction of the video. So let's say we had a one-dimensional metal rod, and let's say before you made the initial conditions that there was a heat distribution of f of x. Now, once you set T equal to 0, you suddenly change your temperatures of the ends to equal 0. So now all of a sudden, this is equal to 0 and this is equal to 0. But the thing is, everything in between is still f of x right after time is 0. So these t equals 0s are going to make all its surrounding points, like let's say this was t equal 10 degrees Celsius, and this was t equals 15 degrees Celsius. Well, this t equals 0 is going to try to make the surrounding points closer to its value. And let's say that t equals 0 Celsius remains at 0 Celsius. Well, if the ends of the bar are held at 0 Celsius, we have to describe how the heat distribution will be at any point in time and at any point on this rod. And for this, we'll need to use a study of math known as Fourier analysis, which is concerned with using the sum of a bunch of sine and cosine functions to describe the distribution of anything. In this case, it'll be the distribution of temperature in the rod. So later in this video, we will find out how to describe the heat distribution in the bar with Fourier analysis. Okay, so remember we had our differential equation. So right now we could just pretend that we have a solution. So we could say u of x and t is equal to x of x times t of t. So we can split u of x and t into a product of two functions of just x and just t. And we can plug this into the partial differential equation. So now we get alpha squared times, oh wait, sorry, let me get a new marker because this one sucks. I really need new markers. So alpha squared x double prime x t of t equals x of x t prime of t. So now what we can do with this is we can divide both sides by x of x, t of t, and alpha squared. So now we get x prime over x equals t prime over t alpha squared. And then thing is, we can't really do anything with this until we realize that both of these must stay constant. And why is that? Well, the thing is, if you change, let's say, either t prime or t, it's not like x double prime or x has to change with it. So if you change either of these, you'll be changing this right term, but if the left term never changes, then the equality is violated, so it becomes an inequality and is not valid. Therefore, both of these have to remain constant, and that constant that they equal to is negative lambda. And you'll find out why I used negative lambda instead of positive lambda later. So now we can create two differential equations. X double prime equals negative lambda x, and t prime equals alpha squared negative lambda t. This creates x double prime plus lambda x equals 0, and this also creates t prime plus alpha squared lambda t equals 0. So these are differential equations that are a lot easier to work with. Okay, in order to proceed now, we can solve these two very nice differential equations we have here. they're ordinary, so we can solve them with basic techniques. So we could say we have x double prime plus lambda x equals 0. We can create a characteristic polynomial for that, so we have r squared plus lambda equals 0. Here we can solve that r is equal to 0 plus or minus square root of lambda times I. And what lambda is lambda is n squared pi squared over L squared. And in this context, what exactly is n? Because I've never mentioned an n before. Well, remember how I said we would be covering Fourier analysis? Well, Fourier analysis is used because we need Fourier series or infinite series of sine and cosine waves. So a solution that is found in Fourier analysis or Fourier series might look something like this. Where n is the term number. And obviously our solution for this heat conduction problem will not look like this. But you get the idea. N is the term number in a infinite series of a combination of sine and cosine waves. So now that we know that, we can find a quick solution for x. So x, since we have an imaginary value, x must come in the form of cosine or c1 cosine of square root lambda x plus c2 sine square root lambda x. But remember, the boundary conditions require that 0, 0 is equal to 0, meaning that, well, at x equals 0, this cosine term is going to be a positive value, and we really can't be having that when, well, it needs to be 0 because this ain't 0. So this means that this c1 over here has to equal 0, making this whole cosine term irrelevant, meaning that only thing that matters here is the sine term. So we'll just say that this is sine lambda x. Remember, lambda is equal to that, so this is equal to sine of n pi x over L. And now we could solve this equation here. T prime plus alpha squared lambda t equals 0. So we can create another characteristic polynomial, but it's really easy to solve. We just have r plus alpha squared lambda equals 0, making r negative alpha squared lambda. Therefore, we will get a function or a solution of t that looks like this, e to the negative alpha squared lambda t. And then, since lambda is obviously n squared pi squared over L squared, we can just plug that in, so n squared pi squared t over L squared. Okay, now that we have our big X and our big T, in order to find u of n, we can just multiply these two together. So now xt is equal to, oh wait, let me switch markers. E to the negative alpha squared n squared pi squared t over L squared times sine n pi x over L. This is equal to u n of xt. But this is not our definite solution because there's an n, so it varies between every n. And remember, we need a Fourier series. This is just a singular term in a vast array of solutions. So our actual function is going to look like this. U of x and t is equal to infinity, from n equals 1 to infinity of cn un of xt. And what this is basically saying is that un x of t is, yes, that's going to be our solution-ish, but we need to have a linear combination of all of these add them up, and then that's going to get us our solution. And what is C of n exactly? Well, there's a derivation for this formula, but I won't cover it for time purposes. But C of n is equal to 2 over L integral from 0 to L of f of x times sine n pi x over L dx. And if these two endpoints are not equal, this looks slightly different. So if u 0, x 0 does not equal that, and it doesn't equal 0 either, well, then it comes in a different form. Cn is equal to constant alpha 0 over 2, which I'll tell you what it is in a later video. 2 over L, then f of x cosine n pi x over L dx. But we won't be concerned about that for now. For now, we can just cover this. So now we have a sort of complex solution. So we have u x t equals infinity n equals 1 of this 2 over L integral from 0 to L f of x sine n pi x over L dx times e to the negative alpha squared n squared pi squared over L squared. Then, oh wait, don't forget the t, times sine n pi x over L. And this is our solution to ux of t. Sorry, my marker pretty much ran out of ink. I need new markers. Okay, so we should probably cover a practice problem, because this is all really confusing stuff. Partial differential equations is one of the hardest things that I've had to study. So let's do a practice problem. Okay, so let's say we have this problem. Find u of x of t if the length of the bar that we're looking at is 20 centimeters. The boundary conditions are, well, let's say we have this bar here. Before any of the heat conduction starts, so t equals 0, everything is at 10 degrees Celsius, every point in the bar. But after t equals 0, these endpoints are both held at t equals 0. But everything else is kept the same. So maybe right after t equals 0, it might still be 20 degrees at the center. Or sorry, 10 degrees at the center. So we need to find a ux of t such that it describes the temperature and its behavior as you travel through x and as time progresses. So we can plug things in. So let's say L equals 20. We already knew that. Well, let's plug it in. So plug and chug. We get series of from negative or n equals 1 to infinity of Cn e to the negative a squared n squared pi squared t over 400 sine of n pi x over 20. Oh wait, right, I forgot to give an alpha squared value. Let's just say that alpha squared is equal to 1 for simplicity. So we'll make alpha squared 1 squared, or this just becomes negative n squared pi squared t over 400. So Now these terms are already good because we can't really do anything to simplify them further. So now we just need to worry about Cn. So Cn, we have the equation that I derived, or not derived, but I showed you guys earlier. So that's 2 over L, our L is 20, 2 over 20 from integral from 0 to 20 of f of x, which is 10, times sine n pi x over 20 dx. So now we can plug everything, or we could integrate. I'm losing my marbles. So 1 over 10, take out this 10. So it's just the integral now from 0 to 20 of sine n pi x over 20 dx. If you take the antiderivative, that's 20 over n pi of cosine n pi x over 20. There's a negative sign, almost forgot that. And then 20, 0. So then this is going to equal negative 20 n pi. You're differentiating with respect to x, so don't forget that. So that's cosine of n pi 20 over 20. So that's just n pi minus cosine of, well, 0. You plug in 0, that's just always 1, so 1. So another way to say negative 20 or n pi, or sorry, just cosine n pi minus 1. Well, when n equals 1, this is, well, cosine of pi is just negative 1, so that's negative 2. And then n equals 2, well, cosine n pi is 0. Or no, sorry, yeah, 0. This is all 0. So this is kind of an alternating series, or negative 1 to the n power. So we can describe this in terms of negative 1 to the n power. So now we have 20 over n pi times 1 minus negative 1 to the n power. So our solution's starting to come together. So we have c of n, and we can honestly just plug that right into our solution, but that would look pretty awkward, and there's algebraic manipulations that can be made to make it look a little simpler. So this 20 over n pi, 1 minus negative 1 to the nth power, can be turned into a piecewise function, because when n is an odd value, negative 1 to the nth will always be a negative value. So this will become 1 minus negative 1, or 2. So when n's an odd value, it becomes 40 over n pi when n is odd. And when n's even, you get 1 minus 1, which is 0. So when n's even, it's just 0. So, you can also write this as the infinite series of 1, 3, 5, 7, ... all the odd numbers of just 40 over n pi. That would be perfectly fine as well. It would just kind of be annoying to write it down like that. So you can do something known as changing the index. So you could set n equal to 2m minus 1. So what this does is, let's say you have m equals 1. Well, this will be equivalent to n equals 1. If you have m equals 3, that would be equivalent to if you have m equals 2, that would be equivalent to n equals 3. If m is equal to 3, n equals 5. So now, if you just make this simple change in index, you can now have a series of just from m equals 1 of 40 over new index 2m minus 1 pi. You don't have to do this pesky odd number stuff in the series. So if we make this change to n, from n to m, we have to change it for everything. So now we have infinity, the infinite series of m equals 1, infinity of 40 2m minus 1 over pi times e to the negative 2m minus 1 squared I squared t over 400 times sine of 2m minus 1 pi x over 20. That's our solution to this problem. And it is a pretty dang long solution, but this is just a small look into the types of stuff that you have to do for higher level maths. So partial differential equations is hard. You get solutions like these, but you're just going to have to overcome it if you ever take the course. Anyhow, thank you for watching. I'll see you in the next video where I'll probably cover the more general case where the endpoints are not even and they're not necessarily set at t equals 0. Thank you.